All right, so taking a look at the during portion. So this is the portion where you would actually have the rubbing happening from the friction. So you'd imagine you take this cotton ball and you're going to rub it on this amber piece. So notice they're showing that the electrons, and there's an arrow pointing in the direction they're moving, the electrons are moving from the cotton onto the amber. So in this case, they're showing two electrons moving, okay? Does that mean that two electrons literally are moving over? No, it's just showing you a symbol representation to indicate that electrons are moving from cotton onto amber. So after the friction has happened and the interaction is over, notice that the amber has extra electrons. So the amber has gained electrons and has become negative. So there's more negative symbols than positive symbols. And the cotton has lost electrons and it is now considered to be positive. So there's more positive symbols than negative symbols. So one thing I want you to keep in mind, the only thing that is moving is the electrons. Notice cotton started with 3 positives and amber started with 3 positives. At the end, you should have the same number of positive symbols. The protons are not moving, only the electrons. So when one object loses electrons, the other one gains them. And notice we didn't have any electrons disappearing. The total number of electrons is still the same. We just literally moved them from the piece of cotton onto the amber, right? It's not like all of a sudden one of them disappeared. The two that are missing from here were gained by the amber. And as I mentioned, the positive charges never move. So how do we know, how would we know if cotton is going to gain or lose, or if amber is going to gain or lose? How are we supposed to know that? So luckily, we have something called electron affinity that will tell us who is gaining and who is doing the losing. Different substances have different abilities to hold on to the electrons. So the higher the electron affinity, the more it wants to hold on to its electrons, and it will actually gain electrons. If it has a very weak electron affinity, that means it doesn't hold on to them very well and will most likely lose them. Okay, so you have a table in your textbook that will show you a list of electron affinity. So this one's a little bit different from your textbook. Your textbook one actually looks like this picture, but all of these charts look exactly the same. They work in the same way. So I'm going to use this one to teach you how it works, and then we'll look at the one that's in your textbook. Okay, so this is an electron affinity chart, or sometimes it's also called a triboelectric series chart. Okay, now how this works is you have a whole bunch of different types of materials that are listed here. Okay, and the order that they are in is very important. So the material that's listed closest to the top are the ones that have the lowest electron affinity. So meaning the items that are closer to the top are very bad at holding on to their electrons. So they lose electrons pretty easily. As you go further and further down this chart, the tendency becomes to gain electrons. So the items that are lowest on this chart are the ones that will be holding on to their electrons the strongest. So when you're doing friction, what you do is you look at the position of the items that you're doing friction with, and then that will tell you who is gaining and who is losing. Okay, so let's look at the amber cotton, for example. So amber is down here, and cotton is higher than amber. So it doesn't matter if it's a lot higher or a little bit higher. The object that is higher in the chart is the one that will lose electrons, so meaning it will become positively charged, and the one that is lower in the chart is the one that is going to gain electrons, so it's going to become negative. And it works the same way for everything. So let's say we were going to do friction with, I'm going to take my pet rabbit and I'm going to rub my rabbit against my head. I don't know. So I'm going to hug my rabbit and it's going to rub all over my hair. Okay. So when that happens, the rabbit fur will lose electrons and my hair will actually gain electrons because it's lower in the chart than rabbit fur. All right, let's do another example. Let's say I took a piece of silk and cat fur. So I'm going to take my pet cat, and I'm going to rub a piece of my silk shirt all over my cat. I'm going to love it. My cat's going to love it. If you know anything about cats, they don't really like, at least a lot of cats don't really like to be touched. But anyways, so let's say we were to do that. Because cat fur is higher than silk, cat fur is going to lose electrons and silk is going to gain them. So there's a whole bunch of different types of charts like this. The only difference between the charts is the stuff that is listed here, the types of materials. The procedure that we just used to look at it, like looking at where they're located, is exactly the same. So you have one in your textbook on page 473. It actually looks like this one, but it works the same way. It's just that it has different materials that are listed. Some are like repetitive, but some are different. So even if you Googled tribal electric series chart, you can come up with like a whole bunch of different types of these because they might have different stuff listed. But the process of how it works will be exactly the same. So let's say we took a piece of plastic wrap and we rubbed it in our hair, right? So plastic wrap is down here, human hair is up here. So that means that the human hair after the interaction will become positive and the wrap would become negative. But remember, let's go back for a second. When they start, so before they interact, it always starts off as being neutral. What we're talking about here when we're looking at the positive and negative, that's the after part. So after you complete the friction. Okay, so let's talk about what happens now after we have this interaction and we have charges. How do the charges interact with one another? Okay, so when we have two objects that have the exact same charge, it actually doesn't matter if they're positive or negative, they will be repelling each other. So positive and positive items will actually push away from one another. Negative and negative will also push away. So they are repelling one another. If you have opposite charges, the term, opposites attract is true with charges as well. So positive and negative objects will attract one another. So think of magnets. Magnets usually have a south and negative section. So the north and south are attracted to each other. But if you try putting two north sections or two south sections together, they repel away or they push away from each other. This is the same concept here. Now, one thing that is not included in this is neutral charges. Okay, so neutral is actually attracted to both types of charges. So neutral will attract a positive and a negative. So basically neutral will attract anything that is charged. Neutral with neutral though does nothing. There's no attraction at all because they both have no charge. So we're going to take a look. Normally I would do this as an example in class, but we're going to do an example that I found a nice little simulator for. So what we're going to do is, this is the end of this here. So let me show you what we're doing. So what we're doing here is we have a sweater. Let's say it's like a wool sweater with a rubber balloon. Okay. So first of all, I want you to notice that we're not interacting anything yet. The balloon has equal positive and negative symbols, and so does the sweater. So the sweater is neutral and the balloon is also neutral. Okay, so let's take a look at our chart to see what would happen here. So we have a wool sweater and a rubber balloon. And we're going to do friction between them. So the wool sweater should lose electrons because it's higher than the rubber balloon. And the rubber balloon should gain electrons and become negative. All right, let's see if that happens. So we're going to take our rubber balloon and we're going to come close and whoa. Okay, look at what happened. The electrons went from the sweater onto my rubber balloon. So that means now my sweater is positive and my balloon is negative. Okay, so maybe if you want to make a prediction, what do you think will happen when I let go of this balloon? I'm holding this right now with my pen. So if I let go of this balloon, the sweater is positive and the balloon is negative. They are opposite charges. So opposites should attract. So if you notice, right? So the positive and negative are attracted to each other. Okay, now that's really the friction concept. I want to show you something that's happening over here that will preview what we are going to talk about next week. So this picture here on the right side is actually representing a wall. Okay, so the wall is neutral. Okay, so the wall is not really an object that you can do friction with. Okay, the reason why is because the wall is attached to the ground. Okay, so we're going to have a concept here that's called basically looking at grounding, and we're going to look at that in our next lesson actually. So the wall is not something that can really do friction, but we can take a look to see what will happen to the electrons when I bring this balloon close by. Okay, so remember, keep in mind, the balloon is negative. The wall is neutral. So if something is neutral and something has a charge, it should attract. Let's see. Ooh. Okay, so the neutral wall is attracted to the negative balloon, right? That's kind of the last thing that we had said. So neutral will attract any charge. This wall is neutral. But I want you to notice what happened when I brought the balloon close. If you take a look, notice the electrons are actually pushing away from the balloon. The electrons in the wall are being repelled. You're probably wondering, well, why aren't the positives moving? Remember that the positives are the nucleus. The nucleus does not move. The only thing that can shift around are electrons. So same thing with the sweater. All of these positive charges did not move because the only item that can move ever are negative electrons. So what we're showing here, this is called an induced charge separation. Okay, so what that means is you are forcing the electrons to move based on the charge that is here. So I'm forcing those negative electrons to push away from the wall or the surface of the wall because I'm using this negative balloon to do that. Okay, now let's say, I can't really bring this here, but let's say I was able to bring the positive sweater here. So let's imagine for a second. Imagine for a second that we have something positive. Let me see if I'm able to do that. No. Okay, so let's reset that. So imagine the sweater doesn't exist and we have a positive balloon. When you have a positive balloon, what would happen here is the negative charges would actually move closer to the balloon because they would be attracted to the positive balloon. So it's hard to show with this example because it's negative and it shows the negatives moving away. And notice, the more negative it is, the more those electrons push away. It's because it's repelled even more so. Okay, so we'll look at this concept again later on. I just want to preview that for you. Really, the main idea here is to show the sweater and balloon friction.